Okay, so we're going to perform some operations with functions today, like adding them, subtracting them. So if you're going to do f of x plus g of x, and you have these list of three functions up here, well, all you're really going to do is add the two functions together. So it's a good idea to put them in parentheses when you write them in your expression, but since it's addition, that's not really going to do much. I've got a couple of like terms. I can combine 5x to the 1/3 minus 11x to the 1/3 and get negative 6x to the 1/3 plus 2. Now subtraction is where people usually mess up. So again, if you are doing subtraction, make sure you're putting your expressions in parentheses, especially the second one that you are subtracting, and then you'll have to distribute your negative and then combine like terms. So on this one, I'll have 5x to the 1/3 minus 2 plus 11x to the 1/3, which is going to get me 16x to the 1/3 minus 2. So nothing super crazy, substitute them in, perform whatever operation it is. This is f of x times h of x, so I'm multiplying them together. If you multiply two terms that have exponents, you're going to need to add those exponents together. So I'll have 5 times 2 is 10, and then I have x to the 1/3 and x to the first. If I get a common denominator, 1 is equal to 3 over 3, which I can add and get 4/3. Okay, now I'm dividing h of x by f of x. So these are just monomials, top and bottom, that share a common factor of x to the 1/3. So I can divide out an x to the 1/3, which means I'll subtract my exponents and have x to the 2/3 left on top. The tendency with these is to go too far sometimes. So if you have, say, h of x divided by g of x, well, on top there's one term, bottom there's two terms. If I have a common factor, it has to be a common factor of all three to be able to divide it out. But there's nothing that divides into all three of those terms. The first two on the bottom doesn't have an x. The 11's not divisible by 2. So just writing them divided by each other is all you can do, and then stop.
Domain of a function is all of your possible input values that you can plug in and still get real numbers out for your output. So the key is you can't have anything that when you plug it in gives you any imaginary numbers, which if you think about it is anytime you have an even root with negative numbers inside of it, you can't include any x values that make that happen. And you also have to get an actual defined value out, so you can't include any values that make you divide by 0. So those are the main things to look for in your domain.
Let's look at a few functions here. So sometimes it's also handy to think about a graph. So if you're thinking about f of x equals 2x plus 3 and trying to determine, well, is there any way I would get a complex imaginary number out or divide by 0? No, there's not, because this is just a regular linear function. It continues in the negative direction and positive direction forever, left and right. Any real number that you plug in is going to give you a real value out. So your domain is just all real numbers from negative infinity to positive infinity. If you look at 5 over x minus 1, we can't have any x values that make us divide by 0. So since there's division here, we have to make sure that we exclude anything that makes our denominator x minus 1 equal to 0. If you set x minus 1 equal to 0 and think about what would make that happen, you can solve your equation and go, well, x equals 1 would make that denominator equal to 0, so we're going to have to exclude x equals 1 from my domain. Any other real number should work, but I have to skip over 1 itself, so negative infinity to 1 with a parentheses, and then 1 to positive infinity. Now we have a square root involved, so if I'm going to only get real numbers out, that means that my inside of my radical has to be greater than or equal to 0. So if you write yourself an inequality and just solve it, be like, oh, what makes 2x minus 1 greater than or equal to 0? Those are the x values that will work to give you real numbers out for your output. So add 1, divide by 2. X values greater than or equal to 1/2 are going to give you positives inside your radical, so real numbers out. One reminder, this was a square root. If it had been like a cube root or a fifth root and odd root, then we'd get real numbers out no matter what, and it'd just be negative infinity to infinity. So quick reminder, we've been working with rational exponents, so this is equivalent to 3 times the square root of x, which means to get real numbers out, I need to be plugging in x values that are greater than or equal to 0. So 0 to infinity is going to be my domain. I can plug in 0 because square root of 0 is just 0. On D, I've got odd roots, if you think about it, because I have a fifth root and a third root. As long as I'm plugging real numbers in to odd roots, it doesn't matter whether they're positive or negative, they're going to give you real numbers out. So I can plug in any value for x and still get a real number, so it's going to be negative infinity to infinity. Say, for example, that you had a square root and a third root, though. The square root would require you to plug in values greater than or equal to 0, so it would kind of override the odd root. One more we're going to look at. So let's rewrite this as, since there's a negative exponent, 1 over, and it's the 1/2 power, so it's the square root of x plus 2. And now typically, to avoid non-real complex numbers, I'd need what's inside my radical to be greater than or equal to 0. However, I'm also dividing by my radical, so I can't divide by 0, so I'm going to need this to actually be greater than 0. So that means x values greater than -2 will be my domain. We looked at domain of just single functions. Now we're going to look at domain of some different function operations. So nice thing on these is whether you add, subtract, or multiply functions together, it's not going to change the domain. Those three are all going to have the same domain. But when you throw in some division, like on D, then we're going to have to check for possible additional restrictions because we can't include anything that would make us divide by 0. So g of x, if g of x equals 0, we're going to have to throw that x value out. All right, so let's start with our domain of f and g individually, because if it's going to be part of a domain of a combination of those two functions, it has to be in the domain of both of them. So for f of x, we can't include x equals 0 because we have 1 divided by x, so 0 would make us divide by 0. Anything else will work. For g of x, we've got square root of 3x plus 1, so it's an even radical, which means we need the values inside of it to be greater than or equal to 0 to get real numbers. So let's write our little inequality here and solve it. Subtract 1, divide by 3. We need our x values to be greater than or equal to -1/3 to give us real numbers out for that one. And then to be part of my domain of f plus g of x, f minus g of x, f times g of x, that combines both of those, our x values have to meet both of these requirements. So we need any x value that is not 0 and also greater than or equal to -1/3. I kind of like to draw out a visual here because it makes it easier for me to think about. So let me do a little number line here. 1, -1. Actually, I have something happen at -1/3, so let's make that 1/3. Okay, so I'm gonna draw in red all the values that work for my function f of x. So everything except 0. So I did a little open circle at 0 because I'm skipping over 0 for my domain there. And then if I look at g of x, the only values that work in its domain are values greater than or equal to -1/3. Now, my values that meet both of these requirements are the places where those domains overlap at. So from -1/3 to 0, and then skip over because that doesn't work for f of x, and then starting back up from 0 to positive infinity. So my domain of a, b, and c is 1/3, -1/3 with a bracket to 0, and then union 0 to infinity. Now I said on D you have to watch out for any additional values that make you divide by 0. So I can't include any x values that make g of x equal to 0. So instead, I have to have 3x plus 1 be greater than 0, not equal to it, which essentially just means I'm going to have to exclude 1/3 itself and use a parentheses instead of a bracket.